Hey everyone! Today we're going to be talking about reading maps and how to become masters at reading all different types of maps. So what we're going to do today is we're going to learn about coordinates, the coordinate system, locating a specific location, as well as using coordinates to find a location. We'll also go over the important features that should be on all maps to make them actually legible and understandable. And then we'll look at finding distances using a scale bar. And then we're going to talk about solar noon and local noon, as well as a bit about our time zones that we have on the globe. So to start, the essential components of a map will be a legend, the orientation, and the scale. So a legend is going to be where the map tells you what the different colors, the lines, the shapes, the symbols mean. So for example, on our campus map, we have part of a legend here. So the parking permit dispenser is at the black star. Otherwise, you would have no idea what this black star actually represented. So we also have a building key part of a legend. So instead of writing out all of these names, we have the different keys here. So here is our science building where we should be taking this class. But we have just an abbreviation and then it is expanded here in the key. There's also always going to be an orientation arrow on a map. So what that means is the map should tell you which direction is north so that you can orient yourself. So most maps, especially if they're large scale maps, are going to have north facing upward or towards the top of the map, the top of the page. However, some maps will be shifted. For example, here's our campus map, and here's our orientation arrow. So here we have north is actually in this direction. So north is this way, and then we have south running this way. So due to the way they wanted to fit this map on the page, they actually shifted the direction so that north was tilted. It's not directly facing upwards on this page if you were to print out this map. And then the last and maybe most important thing on a map is the scale. So there's a couple different types of scales. You can have a written statement, a ratio or a fraction, or a scale bar or a scale line. So I'm going to show you some examples of what I mean by those. So a written statement, sometimes it's called a verbal scale or a stated scale, is something like this here, where it says 1 centimeter equals 250 kilometers. So that means if you were to measure with a ruler on your map 1 centimeter, let's say this is 1 centimeter, that means that the distance of that 1 centimeter is actually 250 kilometers on the ground. The next type of ratio is, the next type of scale is a ratio or a fraction. So that would be this here, 1 to 25 million. Here we have a scale of 1 to 100,000. So what that means is 1 of whatever you measure is equal to 100,000 of that unit on the ground. So here with the stated scale, they switched the units. So 1 centimeter is equal to 250 kilometers. Whereas here, if you measured 1 centimeter, it would be equal to 100,000 centimeters. If you measured 1 inch, it would be 100,000 inches. If you measured 1 kilometer, that'd be a real big map, it would be 100,000 kilometers. So that scale bar can often be seen on many geologic maps. And then the last type is called the scale bar or the scale line. So this is where it's more of a graphic, where we see an actual printed distance on the map, meaning that from this distance from right here to right here is equivalent to 5 kilometers. Or here, this one gives you scale bars in kilometers, miles, and feet. So depending on how you want to look at your map, we see this distance here would be 1 kilometer. This distance here would be 1 mile. So then we can measure on our map and use these scale bars to convert to the actual distance. So to do that, there's two different ways. So we can calculate a straight line distance, which is just the shortest distance between 2 points, or sort of, as they say, as the crow flies. So just a straight line from this point to this point. You can measure with a ruler the distance between them. So here we have a little more than 4.5 inches. And then you can use the scale bar to convert to the distance. So here this is, let's say it's 4.5 inches. And then we go back to our scale bar and we see that if this is in inches, this is 4.5, we can convert it to miles. So you have to use, when you use the scale bar, the graphic, you have to measure the distance between the 2 points and then convert that using the scale bar. So you can make a mark on your ruler. So let's say the point, we're looking at point 1 to point 2. Then you can use this ruler, this distance to convert using the scale bar to see how many kilometers is that actually on the ground. Or you can use a separate piece of paper. That's usually what I do, is I'll make a little mark from point 1 to point 2 and then use that paper down in the corner wherever the scale bar is to determine the actual map units. So how far is that distance on the ground on actual Earth? Now, another way to measure distance is if you're not looking for a straight line, if you're not looking for that shortest distance from A to B here, but you're actually looking, let's say, along a river or along a road. That means you're measuring along some kind of route and the path is not straight. So what you want to do is break that wiggly line into many, many straight lines. So the more line segments you can add, the more accurate your measurement is going to be. So if all you have is a ruler, you can do, for example, here you see if we break this wiggle into 7 pieces, it's not perfectly exact. If we break it into even more pieces, so here we have 13, you can see you capture the shape much better. So the more segments you break it into, the more accurate your measurement is going to be. But really the best way or the most accurate way would be to use a piece of string or thread or something. You can use a phone charger, anything that can be manipulated to follow this path and used to measure how long is that path. So we call it the string method. You can take a piece of string and align it from A to B here, following that perfect curvy line, and then you can measure the length of that string against the scale bar to determine the actual distance along that curved line. So when we're looking at the globe and actually finding a position on our globe, we remember that our globe is a sphere. So we use latitude and longitude to report coordinates and report the location on our globe. So for latitude are lines going around the Earth parallel to the equator. So we have 0 degrees latitude at the equator, and we have 90 degrees north at the North Pole, and 90 degrees south at the South Pole. So our high latitudes are the polar regions. Low latitudes is at around the equator. So from the equator north, we go from 0 to 90. From the equator south, we go from 0 to 90. But we're always going to report as either north or south. Otherwise, you wouldn't know which hemisphere to look in. Now, longitude is the opposite. So longitude is lines that are parallel to the prime meridian. So the prime meridian, perpendicular to our equator, runs through Greenwich, England. That's why it's called the prime meridian. That is where it was first classified. So we have, instead of north and south of the equator, we have east and west of the prime meridian. So for this, we go from 0 at the prime meridian all the way around to 180 east, as well as all the way from 0 to 180 west. So you can either be east or west of the prime meridian. And when we report our coordinates, we always report latitude and then longitude. So 30 degrees north and 100 degrees west, for example. You wouldn't say your longitude and then your latitude. So here are some important features on our globe. Here is the equator. At 0 degrees, here is the prime meridian in that lighter pink. We have our 90 degrees south and our 90 degrees north at the pole. And we have the southern hemisphere is anything south of the equator. The northern hemisphere is anything north of the equator. The others you don't have to be too, you don't have to remember for this class, the tropics or the circles. So when we're thinking about coordinates and reporting our coordinates, sometimes just saying 30 degrees north, 40 degrees west is not specific enough. So if we need to be more specific than a degree, we can break down into minutes and seconds. So in 1 degree, there are 60 minutes, and in 1 minute, there are 60 seconds. So it's just like a clock. And when you see one dash here, this is minutes. When you see double, like a quote, that is seconds. So each degree can be broken into minutes and seconds instead of a decimal. So for example, Saddleback, the college, is located at 33 degrees, 33 minutes, and 10.49 seconds north, and 117 degrees, 39 minutes, and 50.51 degrees west. So that is the very, very specific location of the geology lab classroom in the science building at Saddleback College. So if you want to be specific enough to say, I'm not just looking at the college, but I'm looking at this building and I'm looking at this room within this building, you need to have more information than just 33 north, 117 west. So at Saddleback College, we are about 33.5 degrees north of the equator, and we're 117 degrees west of the prime meridian. So sometimes you can see coordinates with a negative number, and that would just mean that it's the opposite direction. So for example, if you saw 35 degrees north, negative 125 east, that is actually the same as saying 30 degrees north, 125 west. So if you saw negative 35 north, you would know that that actually means 35 south. So this is often seen with the east and the west. You can often see a negative east value actually just means west. So it just depends on how that map or that system is reporting the coordinates. So how do we actually locate a point using these coordinates? So if I give you a coordinate, how do you find it? So the first step is to find the latitude where that coordinate exists. So are we looking north or south of the equator? And then how far from the equator? So once we find our line of latitude that we are located at, then we can find the longitude that intersects. So then we say, okay, are we east or west of the prime meridian? I know I'm going to be located, let's say, on this line of latitude. So where, compared to the prime meridian, am I located? So you find where the two coordinates intersect. That's the position you're looking at. So here is a map of the continuous, or I guess all of the U.S. We have our scale down here. It's a scale bar. We have our coordinates along the side here. So if I asked you to find the state that's located at 40 north, 110 west, you would say, okay, let's look for 40. So here's the 40 degrees north line. Okay, awesome. I know I'm going to be located somewhere on this line, but where? So it's 110 degrees west. So then you want to find where that 40 degrees north intersects the, 110 degrees west line. So we would be located in Utah at 40 degrees north, 110 west. If I had said 40 degrees north, 80 west, we would be right here in Pennsylvania. on that 80 west intersection with that 40-degree north line. So the next thing to talk about is what we call solar noon, or you might also hear it called local noon. So this is the time when the sun reaches the highest point in the sky. So it happens daily. When the sun reaches the highest position in the sky, it is not directly at noon unless you are located at the exact geographic center of your time zone. So the sun is not going to be directly above your head, directly highest in the sky, unless you're at the very center of your time zone. Otherwise, it's going to be offset by a few minutes. So the highest in the sky might happen at 11:55 or at 12:03, for example, depending on where you are located in your time zone. Because the sun reaches the highest position at the very, very center of the time zone directly at noon in each time zone. So what does this mean for us? Essentially, clocks that are in the eastern part of the time zone are going to report solar noon earlier. So if you are in the eastern part of our time zone, let's say we're looking at this blue time zone here with Chicago in it. If you're in the eastern part of the time zone, the sun is going to be in the highest position of the sky actually before your watch says noon. If you are in the western side of the time zone, you won't see the sun in its highest position until after your watch says noon, because the sun at directly noon is going to be right here, the highest position in the sky. So at noon, it's going to be right in the center of the time zone. So as it moves a little bit after noon, remember the sun is moving this direction. As the sun moves after directly noon, where it is in the highest position of the sky in the center of the time zone, as the sun continues to move, it will be a couple minutes after noon before the sun is actually highest in the sky for that western side of the time zone. So this is true for all of the time zones. So the time zones are broken into these regions with really abrupt changes. So it really doesn't reflect the motion of the sun or our rotation around the sun at all. So that's why this can be a little bit, or that's why this is a little bit off. So here I have a map of the difference between the clock and the sun in this red to green scale. So red to green, the green is if your clock is ahead of the sun. The red is if it's behind. So here you can see the eastern side of our time zones are going to see the sun highest in the sky before noon. The western part of the time zones are going to see the sun in the sky after noon, so it's delayed. It's not a huge difference, especially in the continuous US where our time zones aren't massive, but it is important to know. And then here, so this is just the North America, and then I have this whole map, but now I'm seeing that it is a bit blurry, but you still get the concept that the eastern part of the time zone is going to see the sun highest in the sky before noon. The western part of the time zone is going to see the sun highest in the sky after noon. So as the sun moves, we know that the Earth is as the sun moves through our sky, the sun isn't the one that's moving, the Earth is spinning on its axis once per day. So that looks to us like the sun is moving across our sky, or like the sun is actually rotating around the Earth. But we know that is the Earth spinning around its axis. So the sun in our sky covers 360 degrees per day, which means that the sun moves across the sky 15 degrees every hour, or a quarter of a degree every minute. So for example, if you are standing here, At solar noon, the sun is directly ahead with an angle of 0, directly above with an angle of 0. After 1 hour, the sun is offset by 15 degrees. This is 1 p.m. The sun has moved 15 degrees. By 2 p.m., the sun has moved 30 degrees. So at 10 a.m., before noon, the sun will be 30 degrees offset from the highest position in the sky. So in 30 minutes, let's say at 12:30, the sun would have moved 7.5 degrees across our sky. So why is this important? Because we can use it to tell time. So if it is solar noon on our prime meridian, 0 degrees, this means the sun is directly overhead of the locations that are on the prime meridian. So Greenwich, England, for example, it is noon, it is solar noon, the sun is directly above that location. So if you are standing in the US at 90 degrees west, what time is it for you? Knowing it's solar noon on the prime meridian, which is 0 degrees, you are located at 90 degrees west. What time would your watch say? Let's think about that. So the difference in latitude is 90 degrees. So the prime meridian is at 0, and in this example, we're standing at 90 degrees west. So the difference in time would be the difference of 90 degrees latitude, and then we know that the sun moves across the sky. It covers 15 degrees per hour. So 90 divided by that 15 degrees per hour means 6 hours. So standing in the US, you're offset by 6 hours from the prime meridian. So it's going to take 6 hours for the sun to travel 90 degrees. We are offset in this location by 6 hours from noon. And since we are west of this location, that means that our clock time, our watches, are going to read earlier than the prime meridian time. You can remember that. One way of thinking about that is the east coast of the US, the sun rises earlier than the west coast. So we will see the sun rises first, I should say. So the sun rises first on the east coast before it does on the west coast. It's one way to remember the direction that the sun moves across the sky. So the west is always going to be earlier than the east. So if it's solar noon at the prime meridian, it will be if it is solar noon at the prime meridian, it is 6 o'clock in the morning for us at 90 degrees west. It is 6 a.m. So we take that 6 hours and we subtract it. So we are at 6 a.m. It is not yet noon for us in the US. And in 6 hours, it will be. So the sun is going to take 6 more hours to go from the prime meridian to us at 90 degrees west. And in 6 hours from this time, we will have solar noon at 90 degrees west. So here is a map of time zones by country, and in the US, in a couple of the larger countries, they are split into different regions. So we have a couple different regions, a couple different time zones in the US. When you see GMT, that's Greenwich Mean Time, so that is prime meridian time. So you'll notice this would be where our prime meridian is, and that is at a time of 0, and everything is offset from that. So if you are east of the prime meridian, east of this 0, you add hours, so you are later than the prime meridian. So for example, at noon in the prime meridian, at noon at the prime meridian, it's already 8 p.m. in China. However, if you are west of the prime meridian, you subtract hours, so you are earlier. So if it is noon at the prime meridian, it is 6 o'clock in the morning in Texas, because it is earlier in Texas than it is at the prime meridian. So the prime meridian is our 0 point when we talk about time zones. If we go to the east, we add time, so it gets later If we move to the west of the prime meridian, it gets earlier. And then we do have the international date line in the Pacific, where we see the switch from one day to another. That is where the time zones stop, in terms of they go up to 12 hours ahead and then up to 12 hours behind the Greenwich Mean Time or the prime meridian time.